question, I always try to word things the way that I've decided to think about them. So I always like thinking about unit vectors as things that allow me to build in direction. So I can build stuff off of unit vectors easily, right? Because they're length 1, which is awesome. So this one says find vectors parallel to v of the given length. All right, so 54 v is 3, -2, 6. And they want it to have length equal to 10. So what is the current length of v? If its length is 10, then we're done. Right, there you go. But what is the length of v, right? How do I find that? Okay. Yeah, the magnitude of v. Square root of
3.
Square root, yeah, 9 plus 4 plus 36 is 49. That's awesome. That didn't happen very often. A nice whole number length. That's cool. So currently that vector is length 7. How do I adjust it so that it's length 10?
Unit vector times 10. So I take the set.
Yeah, so I first want to find that unit vector, right, in the direction of v. So for it to be parallel to this, and I really want to see if you guys understand, when I write it like this, does it mean that it's a vector that starts at the origin and points to this point necessarily? No. That's sort of the way that we think about it, because they haven't given me any context. They haven't told me where it is. They haven't told me where their origin is. So that's what I kind of immediately think of. But it just has to be a vector. If I did move it here, and of course this is 3 dimensions, but if I did move it to the origin, it would point to that point. Right? So to be parallel to this vector, it just has to be anything in this direction. And I want it to be length 10, so the easiest way to make something have a specific length is to make it first have length 1 and then build on it. Right? So the unit vector is what? How do I get a unit vector for v in the direction of v? What do I do? Yeah, and if you really think about it, a lot of this stuff we get a little bogged down sometimes in the new terminology, we get bogged down in the new symbols, but the idea is just stupid, really. All right, it's too long, divide by how long it is, and then I can build on top. You know, currently this vector is too long. Well, let me cut it down. Let me divide by how long it currently is. Then how long will that have to be? 1, and that's the unit vector. And what do I want to multiply this by to make it length 10?
10.
Yeah, so let's first figure out what the unit vector is, and then just multiply it by 10. Right, and when you scale or multiply, you just multiply each piece of it by that number, in this case 10. So it'll be 3, -2, 6, divided by 7. Isn't that nice? And what vector do I get then? I get 3 7s, -2 7s, 6 7s. And then to make it have length 10, multiply by 10. Yeah. They can't make it any better than that. That's as good as they can make that. Yeah. So I know that a lot of times the concepts are very simple, and that's why I really focus on concepts a lot. At the same time, though, you have to pick up the terminology so you don't get the concept lost under just you ever wonder what it would be like to be in a horror movie? Would you hear that? Like an automatic.
Not the concepts.
It's totally worth
Obviously, try to turn it up, but it's cool if you don't, because I always say that we need a musical intermission. Or in this case, a themed intermission. I like that. So then, the answer here would be what?
37s, -27s, 67s.
Yeah, -27s and 67s. There you go. Cool. I like that. That was funny. So this kind of thing going to happen actually a lot. Because we're always trying to define direction. Well, sometimes we're trying to find a direction based on a given coordinate system. So let me ask you something real quick. If I gave you, here's the coordinate system, and here's I'm just going to put an F because I normally think of it as force. If I said break that down into components, what would that mean that I'm asking you to do? What would that actually mean?
X and Y.
Yeah, in this case, I kind of imply it's two-dimensional, so just I and j. I want you to find out how much of it lies in the x direction, the I hat, and how much it lies in the j direction, the y direction, the j hat. Cool? And that's pretty simple. That's just basic trick. But what if I ask you, if I want to be evil, and I say, okay, here's a vector, no, Jeff, that's not the vector. Here's a vector u, and I want to know how much of that lies in the direction of u, and how much of that lies perpendicular to u. So do you see the question now? So before it was how much lies in the direction of the given axes, and that's always a little easier. It's a little more direct. If I have a set coordinate system and I have some stupid direction that doesn't agree with that coordinate system, do you understand what I mean when I say that? Here's the direction I want, but it doesn't agree with the given coordinate system. Shit. So I want to find this projection, right, for in the direction of u, and then somehow I want to find the perpendicular one for in the direction perpendicular to u. So I'm kind of, in effect, I'm kind of just turning this that way to line it up. Cool. So sometimes I can just turn my whole coordinate system, and that would be some other mathematics. You just create a new, I think I told you earlier, create a new x prime, y prime, z prime coordinate system. That's its own thing. Sometimes you can't turn the damn coordinate system because there's other shit going on over here. I don't want to turn it because then everything freaks out. I just want to write in this one spot of it, do something in a weird direction. So that's what I want to do. That's where the projections are really helpful, especially in 3 dimensions. 2 dimensions is just trig. 3 dimensions, you could break it down to trig, but it would be kind of a long and involved problem. Projections make it really easy. Right? Given a vector f and a vector u, how much of the f lies in the direction of u? Isn't that the projection of f on u? Right? Cool. Okay. I said all that. I can't remember what made me say all that, but there it is. Any other questions from?
Section 11.3, question number 42.
42? Ooh. So what was the main idea in 11.3? What was 11.3 all about? Dot product. Cool. And the word they use, the key word they use in here is find two vectors that are orthogonal. So what's, or perpendicular, is that what they say? Yeah, exactly. So orthogonal means perpendicular thing. What's got to be true about the dot product in order for that to happen? So if I have two vectors, u and v, their dot product has to be what? To be orthogonal. Yeah, it has to be 0 to be orthogonal. And again, I really hate memorizing stuff. I just remember that dot product is like the shadow of one on the other one. When will there be no shadow? When it's not leaning over on top of the other one, right? Either in the negative or the positive. It's just straight up perpendicular to it. There you go. So if there's no shadow, it must be perpendicular. Right? So this is kind of a nice problem because we're learning these vectors and their operations, but we got to go back to algebra where I can force something to happen. You want to find the y-intercept, force x to be 0. You want to find a vector that is orthogonal to, what did it say? Which one was it? 42. 0, 1, 1, right? So here's one way to do this. This is the most direct way to do this. What's this other vector then that I don't know? I want it to equal 0 is for it to be orthogonal, right? I don't know what that is, so
0, -1.
you could just guess this one, right? This isn't that hard. But I'm trying to kind of show you the general way to do this in case I give you a more difficult problem, right? Why is this really not that hard? Because this is nice. This is stupid nice numbers. For the dot product to be 0, what's got to be true about, you know, if this is A, B, C, right? Then what is that dot product? A can be anything, because 0 times A is 0. And then you get B.
0.
So you get 0 plus B plus C. So as long as B plus C is 0, you're golden, right? So some of you guys probably did the problem and came up with an answer without even realizing that's really what you're doing. Because this is 0, 1, 1, this is a nice number. So if I make it 3, 3, then this better be negative 3. So that the 1, 3 and the 1, negative 3, they'll cancel, right? Isn't that what this is? B equals negative C. So there's your infinite number of answers, actually. Do you guys see that? So one way to do it is just to look at it, 0, 1, 1, and just start writing down an answer. All right, well, let's see, let's say 4, 2, and now you got to step back and be careful, right? You can determine it to 2, and then the last one's got to be the cleanup guy that cleans up and makes it 0, right? So what do I have so far? 0, 2. So this one better be negative 2. Exactly. So you can do it kind of without doing the algebra of it. You can just see what numbers work. If I make it a little more disgusting here, you might want to do it this way. And that's really kind of nice, because now I can write, now here's the neat thing, I can write A, comma, B, comma, let me see, let me do it this way I did. A, comma, C, negative C. What the hell is that?
0.
I mean, what does this represent?
Is this vector?
Same thing, it's just more general than that, right? The first thing can be anything, because it dies right off the bat. 0 times that, gone. These two have to be opposites because they both get multiplied by 1 to make them cancel. That's the opposites. So that is actually the infinite number of answers that work here. You pick whatever numbers you want to. Okay, maybe. Okay, cool. That's useful. Okay. Any other questions from? Yeah. Sorry, how much? 11, 3, 54. So this one says. Oh man, this has got a lot of pictures. All right. So 54. Alright, so this has many steps, multi-steps. So step A says find any vector v in the direction of L. Let's see, which is kind of easy. Actually, if you think about it, they just gave me a vector in the direction of L. But you can give me another one if you want to be creative. So so you see this? L has the direction of that. So what's a vector that has the same direction? That. I like it. Right? Of course, if L is in the same direction as this vector is in the same direction as L. So part A is basically stupid. That's all right. We'll deal with it. Part B for this one says, find the position vector U corresponding to P. So, to find vectors, I can either give you 2 points and you find the vector between the two, or I give you a point and the position vector would just be the vector pointing to this point. So, incredibly enough, what's that? That with different symbols on it. Right? So, part A and B are pretty straightforward. Cool. Right. So, before this class, you had points sitting in space. Now you have this class, we have vectors pointing to points sitting in space. It really doesn't seem like that big of a change, but you all know it is. So that's that. There you go. That's the position vector. Part C says find the projection. Okay, cool. Now we got some stuff going on. And I'm going to let you guys do this. So part C says find, which way did it do it? Projection of U on V. So do that. So again, here's, what do they call it? Yeah, this is U. And this is V. Did you do it right?
No.
Do it.
I don't know.
Look up the formulas for that, right? Look up the formula for this,
Which is
Or
over.
find somebody nice enough to remind you what the formula for that was.
That's E. But U on V. So V is in the bottom. So U on V is in the bottom. Yeah. Okay. And then V dot U. Where's V? Where's V? Oh, okay. This is
What?
okay.
Oh, I have it. It's like right here.
0, -4.
Yeah, sure. They said any
What's
vector.
your
So I chose the easiest one. If
V
you want
is
to make it a
3,
unit
0,
vector, let's do
-4. Alright, then let's use
because this guy's length
0,
is
2,
5,
7.
so it doesn't come out too bad. It could be any multiple of this. Yep.
0, 0, -24. Yep.
Where'd you get that?
So it's just -24.
I don't know.
Divided by
Scalar projection is just the length of it. If you multiply that by
so divided by
that'll
5,
be the
right?
direction.
-24.
The length could be any
So
direction.
that's
I want it to be
the
in the
scalar.
direction.
Now I need to find the
V.
direction,
So you gotta multiply
which
that.
is
Hold on, right here.
just. We need to find the scalar or unit vector
I don't know how to get it.
of U. No, of V, unit vector V. So that's just 3 over 5, 0 over 5, -4 over 5, right? It's in the direction. But it's in the direction of the U. Not V.
Yeah. Well, because the way, I mean, again, you can do it whichever way. You definitely don't want to do it the way that has the angle in it, because that would be extra work to find the angle. So you want it in the form that doesn't have the angle in it. Remember, what was this here again?
Magnitude.
What's V dot V?
Magnitude of
something.
squared.
That doesn't
Yeah.
make sense for me.
What?
I know it's.
So we talked about this the other day about, this is not necessarily the way that I would first teach it, but we did a couple problems last time where I said, do you see how at the end it is in this form? Do you see how at the end it is in this form? Because the projection, let me see,
Yeah, at the end is the number.
was this here, right? Alright, let's talk about this real quick. Remember this? This is the one that we've known since algebra. This is the one where it's just getting that last piece of the triangle, right? Okay, maybe. This is making sure that it points in the direction of V, because that's the unit vector of V. Cool. Now remember last time we said, what is this really missing to make it a dot product?
Magnitude of V.
So then this would be U dot V, except it's missing a length of V. Do you guys remember that? Some of you? Okay. And of course this is still the same thing. So then if you multiply it through, you do get, there's your V, bam. This times this is here, bam. And U dot V, of course, is on the top. and I am a little evil when it comes to tests. I will tell you what the formula is if you come up and ask me if you forgot it. I might needle you a bit about it for a minute, but I'll tell you eventually. I'll see how close you are, what you think it is, and then I'll say, no, it's not quite right there, and then I'll get you there. I'm not going to give you the formulas directly. I'd rather you know them. Cool. Or be able to start somewhere. If you can start here, you can kind of build it back up. Okay, so don't think like you have to know them all. You can come up and ask me. I'll try to push you in the right direction. We'll see what happens. So, so just start giving yourself what you need here. What is u dot v? Let me write it down for myself. 026 dot 30 negative 4. Yeah. So what do you get?
24.
Yeah, because you get 0, 0, negative 24. That's awesome. Now what's v dot v, which we said was the same as the magnitude squared, so you don't have to have a square root. Yeah, so v was this, so you get 9 plus 16, 25. I love it. So it's just negative 24 over 25 times v. Right? So that's what the projection is. The projection of u on v will be u dot v, negative 24, over the magnitude squared, 25, times v, which was 3, 0, negative 4. I think the book writes it with that negative 24 and 25 on the outside. I'm used to putting it in, making it a true vector, not a scalar times a vector. It doesn't really matter mathematically, obviously. So that's part C, just to find that projection. And then what's part D?
The third.
Show that W equals U minus. Show that W equal to U minus projection of V, or U on V, is orthogonal to V. Cool, man. So, real quick, let me see if I can't horrify you with my attempt at a picture of this. You've got a point P, a line L. If you take the, let's say, wherever the origin you want it to be, here's the position vector here. So if you find the projection of this position vector onto this, and L is also kind of like V here, right? Is that cool? They point in the same direction anyway. So if you find the projection onto this, and then now what's the, U, where'd U go? U was, oh, I missed this step. Oh wait, okay, this is U, sorry, and this is V. If you find U minus this projection you found, where is it going to be on this picture? If you take U minus this projection, of course when you subtract two vectors, it's the vector that is between them, right? So it's going to be right in here. And isn't that going to, the length of that, isn't that going to be the distance from that point to the line? In general, to find the distance from a point to a line is not easy because it's got to be defined to be exactly perpendicular from the line to the point. So you do have to kind of go through steps to find just what that perpendicular distance is. Right? Okay, cool. Maybe. So do that. Just to remind you guys, U, what was U? U does be 0 to 6. Projection we just figured out was, what do you want to do yourself, Jeff? Negative 72 25ths, 0, what's that? 96 25ths, something like that. Is that cool? That's what we just found. Just multiply that scalar, multiply in there. So if you break it it down. We figured out what that, well, we know what that is. We just figured out what that is. So subtracting the 2 is simple. Yeah.
So, where's W on there?
So W is here. And it doesn't really matter which direction it points. I could have done that either way because I just want the distance of that. Yeah. So there's something I always tell my algebra students that should carry you through all of math. You always break a problem down into its parts. So that's what they did here. They broke down this part for me. They broke down that part for me. Now I just got to throw them in. So what do you get for W?
7 over 25.
Yeah, 0 minus this makes it positive. 2 minus 0
Good.
is 2. 6 minus 96 over 25.
54 over 25.
I love it. So the last step should be to find the length of this, and that'll be how far that point is from that line, officially.
How far?
You have to show that's orthogonal as well.
Oh.
Exactly, yeah. And that'll be nice. That'll actually be easy. Find W. Yeah, the last step is find W, and so we just found W. We want to show that it's orthogonal to V. So how do you show that that's orthogonal to that? Yeah, take W dot V, and it better end up being 0. So let's see, here's W, this ugly business here. And if I dot it with V, V was 3, 0, negative 4. Some of you guys might realize that in a way this just has to be orthogonal, but if you do it, so the middle goes away, there's a 0. 3 times 72 and 4 times 54, same number, different signs. So of course you do get 0. So then W is orthogonal to V. Okay. All right. And the last step is really just find it. Oh, was there something else in this step? Find. So it's orthogonal. Blah blah blah. I like it. And really, the distance is defined to be the closest that this line gets to that point. Because you could say it's this far away, but that's not really fair. All right. If I said how far away from this wall am I, would I say from here to there? How far away from that wall am I? How would I measure it? Perpendicular to that wall. So I want to make sure that I measure this distance perpendicular to that line. Same thing we do in real life. All right? Okay, I love it. 0 reaction. Does that make some sense? Or sit down and stare at it for a while? One key part of this problem. So we got this here. One key part of this problem was if I have some vector and some other vector, doesn't really matter what I call them, the orthogonal projection will be, and what's the definition of an orthogonal projection? It's the vector that does what? Careful, no. It's just they call it the orthogonal projection because this has got to be perpendicular to this. But what's the projection of W on V? The vector that is same direction as V, with the length of this side of what the triangle would be, right? That U cosine theta piece. So this is the part I keep saying is the old algebra part. If you know this and this, you can find that. So you can find this, or this is the trig part, really, if you bring angle in. But the projection of W on V will be this. That's the projection of W on V.
But that's not orthogonal.
They call it orthogonal projection because it's got to be in a straight line perpendicular to what you're trying to project it onto, right? You could actually have slant projections, but we're not going to do that in this class.
No, I mean, this projection is
The projection is parallel to V, I agree with you.
Yeah.
But orthogonal because I'm shining my flashlight perpendicular to this. That's where the orthogonal word comes in. Is that cool? I could have a slant projection where I have to define the angle that I'm shining my flashlight. So I can have an orthogonal projection at an angle of 11 degrees off from normal. What would the slant projection be? I don't think we want to do that right now. Is that cool? So when they say projection for us, it's understood that we have a flashlight straight down, perpendicular to this. Cool. Okay, maybe. Do you notice how I forced this? I mean, in making this has got to be a right, like I just said, it's got to be a right angle, right? So of course, if I find this length, won't that be the distance between this thing and that endpoint for W? It has to be the distance between them. Okay, I got a few converts. I got a few people that look like they want to kill me. That's all right. This happens. As long as you don't act on it. All right. So any other questions from
Anybody else 22?
22 in the same section?
Yeah. It's just visually, I just couldn't understand projection.
So 22. Let me see if I can butcher this picture. So 1, 2, 2, and 1, 2, 3, 1. Okay. V is there, and U is there. And they want the projection of V on U, I mean U on V.
They're at opposite directions, that's why I was
They're not exactly opposite directions. If they were exactly opposite directions, that's a special case, right? Because that would be like the optimal thing. It's lying in the same direction. It's going to be the longest it could possibly be, right? You guys understand that? I mean, anytime I have it at an angle to the other one, it's going to its projection is going to have to be smaller than the actual vector. If I have it lying in the same direction, it's going to be the whole vector. Yeah. So they want us to find. One thing that's weird about this is that leaning over the other vector that I'm trying to find a shadow. I'm trying to find the projection of U on V. So one thing to get over very quickly is that it's not like this. There's not a shadow. If I shine it, there would be a shadow here. That would be a positive thing. Well, if I shine this, it's going to be a shadow that lies on the opposite of V, right? So it's going to be a negative projection.
So you're just continuing.
So do I just continue?
Exactly. So you can kind of mentally do this, and that will be the projection there. I mean, you know, it'll go right here. This will be the projection that we're going to find, right?
And it's going to be negative.
Yeah, it's going to be negative. Negative.
It is almost.
Yeah. So obviously, anytime they say to use inspection, and it can't necessarily be perfect. I think most of these they try to make it land on something nice, but they don't have to. Do you guys see that? Man, just like watching a poker game, and the guy's staring.
You shot it.
Would you want us to be like this? Smiling at you?
That would be creepy. Especially all did the same thing, like. The music would come back on.
Yeah.
But I desperately want you to get this. I mean, here, if I gave you this problem, if I asked you to draw in the projection, that's freaking easy as hell. Do you guys agree with me? Can I say that? So if I give you one where it's just like that, and I ask you to draw in the projection, you just have to do that. So it's going to be pointing in the opposite direction of that vector there, right? So here the problem with this one is everything's kind of like twisted, so just, you know, twist this damn thing. The coordinate system really doesn't matter. This is what you'll learn later, and I'll keep bringing it up every now and again. I can turn the damn coordinate system anytime I want to because I only have this one problem sitting on it. So just mentally do this. And then, I mean, if I turn this around, isn't this V? If I turn this around, here's V. Let me see if I can do this. Yeah, and here's U. Is that cool? So then the projection of U on V would be this negative piece, right? So that's all I'm doing here is I just now turn it, and there it is. Okay. So that's a little misleading when they say it lies on V. And it's not really misleading because where could V be? V could be anywhere here, it could be anywhere parallel to that. So I could just kind of take it and put it there, right? It's got to lie in the direction of V. And I could multiply V by negative and it would be pointing that way. So it's got to be on that line that V exists on, is the way to look at it. Okay. You could back this up with math. Because what is V? 2, 2. And what's U? Yeah, U is -1, -3. So you could go through the whole projection business and see if it comes out close to our estimate. My estimate would be about maybe -2, -2. It looks like they tried to get it right on there. So if you do the projection, let's see if you get -2, -2.
So how will you write the projection? Like, if it's going to be the projection of U over V? Or
Well, they asked me to do this. And I always remember that this is the guy that seems to be on that guy. Whichever way you want to remember it. That, to me, that makes more sense. Because you can't read it as it goes. You can't say projection of V on U. And I try to catch myself when I do. Projection of U on V, because U's on top of V. So, how much does U lie in the V direction? Yeah. Okay. And how do you find the scalar part? Scalar projection.
It's the same
Just
thing.
U dot.
It's the magnitude of that we found, right? Just find the magnitude of the, where'd it go? I didn't write it down. It was -2, -2. Find that guy's magnitude. Okay.
Do we need to find the angle? Or not?
No, they didn't ask for the angle, did they? Yeah. Only they asked for, and the angle would, with respect to what? Right, so they have to tell me.
No, I'm just saying whenever you do the scalar thing, do we need to find the angle?
If you have the angle, you could use a certain form of the formula, right? The one that has the cosine theta in it. If you don't have the angle, then you want to use the form that's got the dot products in it.
Okay.
Yeah. Yeah.
36.
So see, find the component.
So do they ever write it as the projection of V on U?
Yeah, it just depends on what they want from you. They could have asked, what's the projection of V on U? And you would have just had to look at it instead of, then if it was the projection of V on U, and I've only got 2 colors here today, do you see how I'd have to extend U back this time? And then look to see how V falls on it.
Right.
Same idea, just not extending V to see how much U falls on it. Extend U to see how much V falls on it. Is that?
Yeah, yeah.
Same process, just, that's why it's important to know how the hell to read this, so you know you do it the right way.
Sure.
Wait, I had somebody, what was I working on?
Oh, 36.
36, okay.
Can
Oh, this one, go ahead.
you like actually finish the problem?
How do you mean?
It's just the opposite. That's all it is. It's just the opposite of that vector. So it's just negative 2, -2.
I'm sorry, so we got this.
I
We
don't
got-
know.
Anything different with the
No,
formula?
what's the question? We got this for this part of it, right?
Oh, how'd you get that?
Okay, so your question is, what did we just do? So,
Like, I understand how you drew it and whatnot. Are you just supposed to draw it and then whatever it comes close to, you just hit that point?
and it looks to me like they're trying to make it fall right on the intersection and make it nice. Because graphically, it's hard when it's not right on the intersection. And what I mean by that, I mean it's like right on -2, -2.
Alright.
The way that I've drawn it, it sounds like if you do it on top of theirs, it actually does come out that way. Thank God. If it came out some arbitrary point somewhere, holy shit. You know, that sucks. Then you're like, okay, it's 1.8 maybe? No. They try to make it fall right on a nice intersection. So part A to this problem is there's the projection. Part B to this problem, find this length. So it'll be square root of 4 plus 4. Square root of 8, 2 root 2. Okay, cool. So 36. Find the components in the direction parallel to normal to the form blah blah blah. Okay. So they give us a force 0, -10. This is actually what I was just talking about earlier. Give us some arbitrary vector. I want to break it up according to that.
What number?
This is number 36.
The same section.
Yeah.
Yeah, section 11. So a plane, I want to know the components of this parallel and normal to, and I don't know if I use that word normal yet. Normal is yet another word for
Perpendicular.
perpendicular, yeah. So how many words do we have for that now? 3 that we know of. Let me see. So they tell me a plane that makes an angle of inverse tangent of 4/5 with the positive x-axis. The one thing that's nice here is we're in 2D, right? So this kind of problem in 3D would be exceptionally harder, right? So if I draw for myself a little bit of this situation, I've got 0, -10, 2, 4, 6, 8, 10. So here's my F. And I want to project that on, I want to see what lies in the plane that's at an angle of that with the x-axis. So this would be the plane that's kind of cut through here. That's, and actually you can draw this perfectly. Let me see who knows how to do that. If you're drawing this, so this is by 2s here, -2, -4, -6, -8, -10. This is by 1s. Let me see if you guys can get this. Where would you draw a representative vector for this, given that it's got to be at that angle with the x-axis?
Over 4 is x.
Over
next
4.
direction.
Yeah, so this is 2, 4, 6, 8.
5 up 4. Over 5 up 4.
It's y over
Be
x.
careful now. Of course, tangent is
Y over x.
y over x, right? So we could rewrite this and say, okay, the tangent of the angle has to be 4 over 5, which gives you the side lengths. So the 4's got to be in the y direction, the 5's got to be in the x direction, right? So then I'm right there. So here's like here is the cut that that plane makes that they're talking about. Right, so this plane comes in like that, pop, and it makes that cut in my 2D situation. Right? So let me stop right there and let you kind of absorb for a second. I mean, when you first read through that, it's got to sound weird. The plane that makes an angle of theta equals inverse tangent, like, what the freak is going on here? But that's not that bad. You don't have to actually know the angle, because it gives you the side lengths. And that's really how to draw a vector. You just have to know the x and the y pieces, and that's the side lengths. So there's how to draw that plane. So really what they're asking me then is, I want the component of f that lies in that direction and the component of f that lies perpendicular to that direction. Now why do you think they put that in this section? This actually looks almost exactly like a problem we just did. Yeah, it's projections, right? So in general, when I can't break, when my situation gets freaky, I understand a lot of you guys are out there saying, the situation seems to be always freaky here, Jeff. But this is not as freaky. Here's not a freaky situation. Here's a force, break it down into this component and that component. That is a non-freaky situation. Because it's based on x and y axis directly, not some arbitrary weird direction. Right? That's non-freaky easy. If I were to try to do this in 3 dimensions, that gets freaky. Because I can't directly apply trig stuff, you know, as quickly as I can in 2D. That's one example of freaky example. Another freaky thing is this one. If I don't want to go according to the given coordinate system, if I want to go at some angle to it for some crazy ass reason, that also is a freaky situation. So what do we do to save ourselves then to make this easy? We use projections. Find the projection of f on this. And what is this vector? I know they said it's a plane at an angle of crap, but I can now look at it as a vector in my system here, right? What's the vector? 4, 5, 5, 4, sorry. Right, 5, 4. So now just find, and of course this they gave you is 0, -10. If you find the projection of this on this, that'll be in the same direction as that. And let me say a quick word about two-dimensional. This is kind of funny because I wanted to talk about this anyway. I wasn't sure where to put it, and this is a perfect place to put this. Before I talk about this, go ahead and try to do that. Try to just find the projection of this on that. So the projection of, and how would I write that? The projection of f on v.
Little v, big F.
Little v, big F. I like it. So do that. So really, in an example, the equation we have, just replace u with f. You'll be fine.
Jeff,
Yes.
why not projection of V over it? How did you choose this?
Because I'm trying to, what am I trying to break up into components?
V.
What are they? Now be careful. What am I given? I'm given a force, right? Oh, which one was this? Oh, here, number 36.
Oh, yeah.
Find the components of the force. I'm trying to break that up. So one a component of this that's in this direction. So the force, how much does it lie in that direction? And then I'll give you a nice shortcut for two-dimensional perpendicular vector. When you see it, hopefully you'll go, well, duh. I know some of you are thinking, I'll never say that phrase in this class, but
Yeah, 31.
yeah.
That's
So what are you guys getting for v dot f? 5 times 0 is 0, plus 4 times negative 10 is negative 40, so negative 40. What are you guys getting for V dot V?
41.
Yeah, so that would be, here's V, so it'll be 25 plus 16, 41. We don't have to square root it because that would be the magnitude squared. So that's 41. So now I just got to throw everything in there. So I get V dot F was negative 40. V dot V was 41. V was 5,4. So if I really want to bring that in there. Why does it make sense it's negative, negative?
It's going the other way.
Yeah, because the projection would be in the opposite direction. I love it. So it'd be a negative, negative answer back here. Cool. All right, so that's part of it, right? 'Cause that's the parallel component, parallel to V. Now, let me take a second here. So this is F parallel. I can't remember exactly which one this book uses, but you can make F parallel, and very often we'll say F tangent, or F normal, you can say, whatever. F orthogonal with a little O.
Can you draw the projection in it, so it's gonna be.
Yeah, so this would be extended back this way, and then this has to be at a, what's got to be true about when I draw this, it's got to be at a right angle, right? And so this is the piece we're talking about. So what we just found was this. Is that right? Because think about it, how close is this to being perpendicular to this? Very close to being perpendicular. So the actual projection on that should be very small. It's almost nothing. And that is, well, I don't know. Is that small? Sure. Now, let me take a step out of this problem for a second and give you a nice, easy problem to look at to get the idea of something. If I have a vector, let's say, negative 3, 4. Can somebody give me the vector that's a vector that's perpendicular to that? We had a problem like this earlier that was in 3 dimensions, actually, sort of. One of them was 0, but that's all right.
4 and 3.
Now be careful, don't make it 4, negative 3. Why would that not be quite right? I know.
So that'd be double
I think I heard it right over here. Yeah, you want opposite signs at the end. So it'd be 4, 3. Now take a second and think. How are perpendicular slopes related? If the slope of a line was negative 2, what's the perpendicular to that? 1/2, right? So what is this slope here? What is the slope?
Negative 4.
I mean, 4 over 9.
Don't make me cry. Okay, negative 4/3, right? Because you've got to fall 4 and go over 3. What would the slope of the perpendicular line have to be?
Switch it.
3/4. Isn't that what this would be?
Yep.
Wouldn't that vector be the vector 3, 4, or 4, 3, sorry? Whoop. Make this right angle 4, 3. And that, of course, would have a slope of 3/4. So really, the way a shortcut for 2D, 3D is not quite this easy unless one of them is 0, and you saw that already. Shortcut for 2D is just take it, turn it, and change one of the signs, right? Because then you're guaranteed to have a dot product that is, what's got dot product got to be for right angles? 0. So that guarantees you a dot product of 0. Negative 12 plus 12, 0. That kicks ass. So now we got the part that's parallel to the V, right? What's the part that's orthogonal to the V? Going to be?
Negative 160 to 100.
Yeah, all right. You could do negative 160 over 41, 200 over 41. And actually, to be a little more careful, orthogonal to V should be like this, right? So technically, which one should be positive, which one should be negative? The x should be positive, the y should be negative. Mathematically, it doesn't care. The projection, I mean, the dot product is still 0, but you want to make sure that with your picture, it's actually pointing in the right direction. Now the thing that's not quite there on this though, let's double check this. So what's the thing about that? Is that the right length? No, right? So a really cool, so do you guys see how I've got the direction correct? What I can do, what did we do to get the parallel piece? We did F dotted with V. And we actually did the projection, so that was what we did. What is orthogonal to V? What would the vector be that's orthogonal to V? Yeah, it would be if I drew it, and it's got to be kind of like in the direction I want to go. So it would be negative, it would be, it would be 4, -5, right? The vector that's orthogonal to V would be 4, -5. And then I can just do the projection of F on that. And then that would give me the right length. So if I want to find, I could do the same whole procedure using a vector that's orthogonal to this. And that will guarantee that it's orthogonal, the orthogonal piece. It'll have the right length. Maybe.
Why can't
So-
we use this answer? The one that you just
Because this is the right length for that piece, but shouldn't the orthogonal piece be longer? Because more of it is in that direction?
We can just find the distance between vector V and the projection. That's going to be the perpendicular.
Yeah, like we did in the last problem, right? Like we did like we did with the U minus the projection,
Yeah.
right? You could do that too, I love it. That's more direct. So you can take F minus the projection that we just calculated, just like we did in that last problem. So you could take F minus this projection we just did. That would also work. Cool, I like it. Okay.
That's easier.
Yeah, that's easier. Okay. Real quick word on this. Which one was that again? That was number 36? Oh, let's see if they have a, I don't know if they really have an example exactly like that one. But they have like example 3, which is orthogonal projections. They have example, no, they have an example quite like that one though. Okay. Oh, here we go. Example 5 is, yeah, example 5 is almost the same thing as that one. They have it on a block, but still, it's the same kind of idea. You have a force straight down, and you're trying to put it, project it onto a vector that's going diagonal. So example 5 is exactly like that one. Let me see. All right, let's get into some new stuff. And I think you guys are trying to figure out, my method of operation is always trying to show the idea behind the formula, or at least give you a physical example of what's going on. So here's a good example of what we're about to do. I have a little notes for myself to keep straight. Let me just do this and make it too pretty. What's the area of that shape? And actually, I want you guys to take a minute and try to figure it out. It is not AB. Make sure nobody tells me that.